Welcome back to DR Electronics. In today's video, I'm going to be covering a breadboard adjustable power supply that I recently designed. Now, the reason why I made this was because I wanted something that I could use quickly and efficiently rather than the bench supply that I have that can go up to 30 volts. It takes up a lot of space, and I wanted something that could have 5 volts, 3.3 volts, and up to 15 volts adjustable output. I do have a breadboard power supply from an Arduino kit, but it only has 5 volts and 3.3 volts available. So that's why I made this. This video is mainly just going to be covering the schematic and some of the mistakes I made regarding the feedback calculations for the boost converter. The second video will cover the layout and demonstration of the newest revision of this board. But let's jump into the schematic here. We'll start with the USB-C section. So mainly what we have is essentially a 5 volt input with two 5.1K resistors on the CC1 and CC2 lines. These are required for USB-C power operation. We also have a 1.5 amp fuse here, and it is a resettable fuse. So I made sure that the maximum voltage that this fuse can withstand is 5 volts, as we don't want to exceed 5 volts for our input supply. And the hold current is 750 milliamps with a maximum of 40 amps and a trip current of 1.5 amps. So the fuse itself won't start to reset and no longer allow current to flow in the circuit until you reach that 1.5 amp threshold. And we can see this in the datasheet here, with the letter F being the part that I selected. So if we follow the curve here, we could see that at 2 amps, we have roughly a trip time of 0.250 seconds. So this means that it's pretty quick in terms of reacting to the amount of current that's flowing through the system and essentially protecting the rest of the circuit. I don't think I'll need a faster time for this circuit, and a lot of the projects that I design tend to fall in the range of 100 to 500 milliamps of current consumption. So this is more or less just kind of like a safety proof mechanism, just in case for whatever reason the supply that I plug in to my breadboard supply is higher than the expected voltage. So I have that, and I have a TVS diode here, which I also used from LCSC. Most, if not all, the parts for this board were provided by LCSC through JLC PCB. Big shout out to them for giving me a coupon for this project. I was able to get the boards assembled and manufactured for them. But this TVS diode essentially kind of acts similar to the fuse, as it's used for ESD protection along with over voltage protection. The breakdown voltage for this is 7.5 volts. So again, even if the fuse for whatever reason doesn't reset, if you have a voltage at 7.5 volts or higher for whatever reason at the input, the TVS diode rather, will start to conduct in the opposite direction, and most of the current will flow to ground as opposed to the rest of the circuit. So that was more so for ESD purposes. The fuse is for overcurrent and over voltage protection. But that's pretty much all that's involved here. The main part of the circuit that's really important to emphasize is the boost converter and the LDO regulator. Though the LDO is quite simple, there are still specific key parameters that I wanted to keep in mind. So we'll go through that, and also the mistake that I made with the feedback pin and some of the calculations that I did in order to determine what the maximum possible output current could be with a 5 volt input and a 15 volt output. Before looking at the boost converter, I wanted to quickly cover the LDO regulator. So it's pretty simple. All you have is your input voltage, which is 5 volts coming from your USB-C connector, and your output voltage, which is a fixed 3.3 volts. This then ties to a jumper with the ability to select between 5 volts and 3.3 volts, which is then connected to a rail in which that has a 2.54 millimeter pin header, which snaps into the breadboard. So in the case of the LDO, all I have is an input capacitor and an output capacitor. I don't have a power status LED, as I put that in front where the USB-C connector is. So there's really no way to verify on the board itself with a status indication that there's 3.3 volts, but you could always just check with a multimeter. And I used 22 microfarad capacitors because the boost converter in the datasheet recommended 22 microfarad caps. And for BOM consolidation purposes, I figured it was just easier to use that, as with LDO regulators, you don't have to have a specific capacitor number. Typically, the datasheet will just tell you a minimum value that's recommended, which in this case it did on page 2, which is 4.7 microfarads. So 22 microfarads is well above that threshold, so that shouldn't be much of a problem. One other thing that you should consider with LDO regulators is the load regulation and the transient load regulation in terms of stability. So the way that you can make sure that your LDO is stable is by keeping your capacitors as close to the IC as possible and making sure that those caps fall in within the minimum recommended range. And other than that, just keep in mind the thermal considerations. So if you are driving a lot of current on this, you may want to use a copper pour for your traces, or you're going to want to use some sort of thermal vias in order to dissipate the heat. But in my case, since I'm probably only going to be using this for I2C and SPI peripherals, which barely use any current, the 1 amp current max ability of this IC is more than enough to withstand than what I need it for my projects. So the boost converter is what I consider the most important part of my schematic, as I already have an STM32 and Arduino that can give me 5 volts and 3.3 volts input. So the converter I selected for this was the SB6286. It's an LCSC part that's basically a repackage of the MT3608. It can provide up to 2 amps of current with a 1.2 megahertz switching frequency, and it has an output voltage of up to 28 volts. So the 15 volts is well within the range that we're expecting. The feedback pin can withstand a maximum of 6 volts, and we have a peak switch sync and source current of 4 amps, which is quite high. So pretty much what I did was I took the basic application note and I copied it into my circuit. However, the only difference that I wanted to do was make the supply adjustable, because with this current configuration you have 2 fixed resistors which provide a fixed output voltage. Now, originally when I did this calculation, the way that you do it is essentially you take the feedback reference voltage, which in this case is 0.6 volts, and you multiply that by 1 plus the top resistor over the bottom resistor. So when I originally did the math, I set the bottom resistor to 10K and I solved for R1 and I got 200K. Now the problem is with the way that I configured the circuit, I did not translate the math that I did onto the schematic. So essentially what you have here, and I could show this in a Fallstad simulation, the supply never exceeds 5 volts. In fact, the maximum voltage that you could have with this given setup is, I believe, 3.8 volts. So basically what you want to do with this when determining what output voltage you want and the resistors that you need, you essentially need to do some algebra in order to solve for R1. So you first divide by your reference voltage, you subtract 1, and then you multiply the resistance in order to figure out what R1 is going to be. And this can also be seen in the basic calculations of a boost converter's power stage. I've referenced this document before, but for people new to the channel, I will provide a link for it in the description. But that was my issue with the setup that I had. Now, I've only made fixed boost converters before, so this is technically the first time I was doing this. So it's not really surprising that it didn't quite work. I thought originally with the first revision of the first initial release of the schematic, I had the Schottky diode pass the resistors here, which is incorrect, as if you can see in the actual application example, the Schottky diode is supposed to be before the resistors, but I put it after, so that's another mistake that I made. I thought that was the reason it wasn't boosting initially. That was definitely part of it, but the feedback resistance here is just completely wrong. So the proper way to do it with the 200K potentiometer is, instead of making a voltage divider here, you use it more so as a variable resistor, which is what I intended to do originally, by taking the wiper pin and connecting it to the bottom pin of the resistor. And then instead of using two 20K resistors at the bottom, you use one 8K resistor. And from there, if I adjust the resistance, we could see we have a maximum possible voltage of 15.5 volts with a minimum voltage of 4.7 volts. So that was the mistake I made with that. I ended up making it twice because the second revision I didn't really change this. I kind of left it the same. So now I know this for the future, but this is just something important to keep in mind if you want an adjustable converter, that the internal reference voltage along with how you set up the voltage divider ultimately determines what your output voltage is going to be. For part selection of the boost converter, for the capacitors, I just made sure that the voltage rating of these was higher than the expected maximum output voltage. So in this case, I was expecting a maximum of about 15.5 volts, which was seen earlier in the fall stat simulation. So I chose capacitors with a rating of 25 volts, and these are also the same for the LDL regulator. I put a 1K resistor on the enable line if I want to pull the converter low while not removing the 5 volts from the USB-C connector. I could just remove this 1K resistor and solder it off the board. The inductance I selected was also based off the datasheet. The datasheet recommended a range of 4.7 to 22 microhenries. So I chose an inductance of 10 microhenries, and it has a current rating of 1.4 amps with a saturation rating of 1.6 amps. The DC resistance is also fairly low, only at 305 milliohms. And if we look further into the actual data sheet here, we could see that the inductance is not affected by our switching frequency of 1.2 megahertz. And looking at the inductance versus DC current, we could also see that the red line here for 10 microhenries also isn't affected much by the maximum expected output current or current draw for a circuit for us, which is about 1 amp. So it goes from 10 microhenries to about 8.5 or 8.8. So that's also good as well. The Schottky diode that I selected for this project also has a voltage drop of only 550 millivolts. It's rated for up to 2 amps, and it has a voltage rating of 40 volts. So I just wanted to make sure that the forward voltage for this wasn't too high of a voltage drop, and that the current rating was also high enough for it to withstand whatever current was being drawn from the circuit. I did some calculations here in a spreadsheet in which I took the expected efficiency for this converter. I rounded it down to about 85%, and then I determined the maximum switching current of my device, which in this case would be about 0.3 amps or 300 milliamps. So keep in mind, this is with an expected output voltage of 15 volts. We can expect the converter to be able to withstand a maximum output current of 1 amp. Now, if we have an output voltage of 9 volts, the output current goes much higher, goes up to 1.8 amps. And if we have a Vout of 7 volts, then we have a maximum output current of 2.3 amps. I'll also try and provide a Google Docs or spreadsheet that can be available so that you could see how I essentially made the formulas for this and did all the calculations. But again, this is based on the Texas Instruments document that I mentioned earlier, which just goes through the necessary steps that are required to figure out how much current your IC can withstand given the input and output voltage discrepancy. So in this case, it's going to be about 10 volts going from 5 to 15. So that's why it can only withstand up to 1 amp. But if the output voltage is lower, then it will be able to withstand a much higher current draw. So that's going to be it for the first part of the breadboard power supply. The second part is going to cover the layout and where I went wrong with the pin header dimensions and spacing, and it's also going to show you the new layout with the revisions of the feedback pin. So if you haven't already, be sure to check out my other videos. I cover some programming, hardware, STM32 setup, along with other projects that I've made and some of the corrections and mistakes that I did so that you can be aware of these for when you design your circuit boards. But as always, thank you all so much for watching and have a great day.